Questions? Yes?
So, what performance hit do you see compared to like a sort of insecure?
Okay, so for the operating system kernel, so with memory safety, we're currently seeing performance tests that are so high right now that I don't actually want to talk about them. Our current research work is to get those overheads down. So, Vikram, do you remember the numbers for the application programs?
Yeah, so it varies from the vast majority of programs. It varies from about 0 to 20%. There are a few that we've seen that go to 25 to 30%. There's one we've seen that goes to 90%, and that's a scientific program that's array intensive. It has this array reference inside a 4D loop nest, and I think we were only able to pull it out one loop or something, one or two loops, I don't know how far, but not all the way. And so we will run across cases like that where you have significantly higher overhead. But all of the systems code we've tried, like DBs, the overhead has been extremely small. In many of them, it's like less than 5%.
Are you using any of the sort of processor primitives for doing sort of process space isolation? That's some of the old.
What kind of primitives?
You have some of the things that are being used in things like corner scan.
The only thing we do is for, and actually that's not even turned on in those experiments, for detecting dangling pointer errors, which is sort of an orthogonal piece to all of this because we don't turn it on by default. We use page protection. It's just standard MMU stuff. Actually, I'm sorry. For the array bounds overflow, also we use page protection. So there are a couple of places where you have to allow a pointer to go out of an object. As long as it's not used, that's okay. And then it comes back into the object and then gets used, and that's legal. But we use, while it's out of the object, we use page protections to make sure it doesn't get dereferenced.
So, I'd like to actually talk a little bit more about what you'd like to do with this, because the application you talked about could readily be done in a VMware style virtualization, and now I don't have to worry about compilation issues with having a series compiler.
So are you talking about using VMware to isolate applications?
This whole software segmentation of the memory, I mean, so you modify the kernel memory allocator, right? So you don't have to do that anyway, but you could easily invoke some set of, no-op instructions that this is what's often done with these kind of virtual machines, that the hypervisor recognizes as some kind of command. So you basically transfer information on the software segmentation to the hypervisor. So the application that you showed right here could actually be done in something like Zen or VMware or whatever.
I'm not certain what you mean.
You're using this to do better. The application you gave us memory protection. Right.
Well, what it is it's being able to do efficient array bounds checks.
Sure.
And pointer checks on memory references.
And the efficiency comes because you use the static analysis to prove that certain things can't violate those.
So there's two components. We use analysis to determine that certain memory accesses are type safe.
Sure.
We also use it to determine which objects can alias. Right. So if I want to move back to the slides, if I want to do a runtime check on this loop pointer. Right. So previous techniques like secure, I think it is, what they would do is they would have one large data structure that recorded every memory allocation, and you search through all of them. The speed up that we get is because using pointer analysis, we know, for example, that these two pointers can never alias. So this pointer, we know that this pointer can never point to this memory or that memory, etc. So instead of having one data structure which contains all the information on memory allocations, we have multiple ones, and we can always check the right one.
Okay, so I buy that, but where does the virtual architecture come into place? I mean, couldn't you just instrument the runtime to do this instead of relying on some virtual architecture?
So the advantage of the virtual architecture. So first off, it gives us additional type information. So when we're doing this stuff, it definitely helps because this allows us to determine whether memory accesses are type safe. It also allows us to be able to tell the difference between an integer and a pointer inside of a data structure. So if I load some particular value, I know whether or not I'm going to use it as a pointer. So
if I just add one word to that, I think the right way to think about this work is we're trying to make it look like we're writing a kernel in a safe programming language. So there's been research projects on doing that, on writing kernels in the early Lisp machines, in Modular 3, in Java, in C#. If any of you have heard of the Singularity project at Microsoft, they're writing it in C#. The problem is none of that research extends to today's operating systems like Linux and BSD and Mac OS and Windows. These are written in C or C and C++. And so what we're trying to do is provide an environment here that what we call a safe execution environment. It gives you close to the guarantees that a safe language gives you. It's not identical because we don't do garbage collection, and so you can actually have dangling pointer errors. And in fact, I think one of the main sort of intellectual contributions of this work has been to show that even with dangling pointer errors, we can do sound static analysis on the programs. We can preserve the guarantees of array bounds checking, of partial type safety, and so on.
So where is the contribution of LLVM? My understanding is you use it as sort of an intrinsic expander because you have all these intrinsically defined, and you let the LLVM virtual machine expand them. Then you talk about static analysis and pointers. Do you really get, like, is it done by the LLVM or you wrote your own module to do static and pointer analysis?
the pointer analysis is an LLVM pass.
Or is it LLVM?
Yes, it's an LLVM pass.
It's out of tree. It's out of tree. It's essentially the current descendant of Chris's thesis work.
But it's in a publicly available CDS model.
Yes.
But
So the full alpha model is already one.
so we should wrap this up. But I think that there's lots of comments and questions that can be taken offline.